Hello. We will continue today with discussions of solving wave equations, partial differential equations. I recommend that you look through some of the other techniques, because today we do a more complicated one than we have before. So look at waves with strings, if you haven't already, before we talk about this. So today we'll talk about solving the time-dependent Schrodinger equation. So these will be another wave equation using similar techniques, but a variation of them. So it'll be complex waves, complex because they have multiple parts, and it'll be a wave packet because that's what's so interesting in quantum mechanics, and that's what we'll talk about. So let's talk about it. The problem assigned to you, if you want, for this problem, for this chapter, is to say, what if we have a particle, an electron, confined to a region of space, and the region of space is of atomic size? Okay, that tells us immediately, number one, it's an electron, which is a light particle. Number two, if the region of space in which it's confined is of quantum size, which is atomic size, then we need quantum mechanics. Okay, now we're also told that the particle, the electron, has a well-defined momentum and a well-defined position. And that means we need a wave packet to describe it. Okay? Because ordinary quantum mechanics that you see so often, the time-independent versions, have particles of definite energy, okay, or maybe a definite momentum, but not also a definite position. Here we want both, so we need the real Schrodinger equation, and that's given here in equation 1. And I call it the real Schrodinger equation, or Schrodinger equation, not because the equation is real. In fact, the equation is not real. It has a complex term. It has an imaginary term here, I, and it has a time derivative. But this is the real Schrodinger equation because this is the equation that Schrodinger wrote down. He didn't write down the time-independent version. He wrote down a time-dependent one. When you talk about relativistic quantum mechanics, one always has to start with this time-dependent version because space and time are, after all, related. So this is a good equation to study. It's another good example of computational physics because traditional physics education tends to ignore the time-dependent Schrodinger equation. In fact, much of physics has, because it's hard to solve. It's hard to get the time dependence in a general case. One is reduced to, in almost every single case, solving it numerically. But for us, that's fine. That's just what we want to do. We want to see how to do that, and now we can go ahead and do it. So, if we have a state that's not of definite energy, in other words, it's not an eigenstate of the Hamiltonian, so the wave function does not separate into a space part and a time part, if that's not true, then we have to solve this full time-dependent equation. Okay? So, for our problem here, we have a localized electron of definite momentum. We model it. This is now beginning the solution. And the model is to say, okay, we start off at time 0 with an electron of momentum k0, if you want wave vector, but I use units in which h bar is equal to 1, so the momentum wave vector are the same. So this particle has a fairly well-defined momentum of k0, but it also has a location here. As you can see, this is an exponential x squared, so this is a Gaussian peaked at 5. So it's a wave packet. We're starting off with a particle. It doesn't have time dependence built in yet, but it'll be a wave packet. We're starting off with a particle that's centered at 5, but is moving like a plane wave with an amplitude. Okay, so that's our model solution to begin with. And note that if we have the right-hand side of the Schrodinger equation, the h psi part, which means we take the second derivative with respect to space and we multiply by the potential, the right-hand side of equation 1 acting on this baby here, which has an x here and the exponential, a Gaussian, has a plane wave, will not give you an eigenstate of energy. It doesn't give you just a number back times itself. It gives you something more complicated. So we don't have an eigenstate. We need to solve the time-dependent Schrodinger equation. Okay? Here we say, okay, here's an applet to show you these. We do this, and we have lots of applets here. So this is a harmonic oscillator. So what we're talking about is a wave packet. This is a harmonic oscillator wave packet. And as the case in point here, this wave packet is actually moving in a potential which is a harmonic oscillator, so that the Gaussian is a good approximation. And if we look at the solution, we see the wave packet changes, it stops, it rolls back and forth, but it doesn't really change its shape much. But that's a special case. Okay? So we can stop this, but this is the wave packet we're trying to solve for. It's obviously time dependent. You can see it moving now, and it's obviously space dependent. And here this just, the controls, we can make the well flatter, we can make it sharper, we can make it higher momentum. So this is an applet, it's on the CD or the DVD or on the web, and it just runs back and forth, runs every time. So stop, I'll kill that. Okay, so look at the next slide. So in the next slide, we talk about the kind of algorithm we need to solve the Schrodinger equation. So we have a wave function which we assume has a real and an imaginary part. And you can ask yourself immediately, hey, I've taken a lot of quantum mechanics. We just always assume real wave functions. Well, yes, that's true if you only have time-independent Schrodinger equation. You only have a pure real Hamiltonian and a pure real Schrodinger equation. But here we have a time derivative which has an I in it. So this I, d psi by dt, requires us to have a wave function that has both real and imaginary parts. So that's where it comes from. So let's assume that we have a wave function that has real and imaginary parts. If we substitute it into the Schrodinger equation, which is on the previous slide, what we get is now two coupled partial differential equations. Okay. They're both space derivatives, second derivative in space, first derivative in time, and then they have a potential term. And what you see is equation 2 here tells you that the time derivative of the real part of the wave function is determined predominantly by the Hamiltonian acting on the imaginary part of the wave function, and the time derivative of the imaginary part of the wave function is determined by the Hamiltonian acting on the real part. So they're coupled. So you simultaneously have to solve a complex set of coupled equations. Now, historically, people have said, okay, it's a wave equation. It's not the same wave equation we solve with a string. Remember, that has second derivatives in space, but it also has second derivatives in time. So this is a wave equation with only first derivative in time, second in space, but it's still a wave equation. Why? Because it produced waves. No big thing. So what has been discovered in time is that in quantum mechanics, it's nice, it's important. One of the premises is that the probability is conserved. Well, if you take the solution of this equation for very long times, using just the technique we used last time for a string, what you find out is that the integral of the probability density, which is the modulus of the wave function squared, integrated over all space, is not necessarily conserved very well. So we need a better algorithm. Okay, so we're telling you that ahead of time, because why go through the historical problem of doing it wrong? We'll do it right first. So we need an algorithm which can guarantee very good probability conservation. Because it's sort of bothersome if you're trying to discover new quantum physics and you don't know if one of the premises of quantum mechanics is being made well enough, and that's what's causing the problems. That's what's happened. So we'll look for a better algorithm, and that algorithm is known as a staggered time algorithm. Okay? So this term is used often for wave equations, other partial differential equations, particularly ones with multiple parts. We'll see that again when we talk about electromagnetic waves. And what this does is it says staggered times means that we have two times at least, and we'll solve for the real part of psi at time 0, time delta t, time 2 delta t, where delta t is the step size in time. So it'll be the leapfrog technique again. We'll take one solution, move it ahead one step in time. But the imaginary part of psi, we won't solve for at time 0 again. We'll solve for that at half t, and then 3 halves t, 5 halves t. So it'll be, again, time steps of delta t, but the times will be separated or staggered by a half a step. And the reason for this is when you take the real part of psi and the imaginary part of psi and you put them together to construct the density, it turns out that 2 orders of error of error cancel, and we're left with a higher order algorithm for the probability conservation than we would have if we just used previously. So it's like Runge-Kutta, where you can get, by choosing the derivative in different places, you get cancellation. Here, by choosing the real and imaginary parts evaluated at different times, and you look through the Taylor expansions, when you add up the real part of size squared, imaginary part of size squared, you end up with a density which has terms canceling. The error cancels. So that's the whole idea. We won't go through all those applied math details, but we'll talk a little bit about how we do it. So look at the next slide, please. So we'd like to develop this staggered time algorithm, and it's still based on finite differences. So we imagine space separated into position x, so we're doing a one-dimensional problem. The same exact technique worked for 2, 3 dimensions. And we have time running down here on the ordinate, okay? And we have a lattice, as before, space-time lattice, and we have white dots. So what white dots would correspond to the initial, at time 0, the initial conditions on top, first order in time, and then we have boundary conditions. We need boundary conditions to solve the partial differential equation, and the boundary conditions, of course, could be whatever you want. They could be the wave function vanishes on an edge, you put it in a box. They could be periodic boundary conditions. Okay? And you could choose both. The boundary conditions should not have an effect on the interior solution until you get close to the boundaries, that is. So the real problem, of course, would have a much, much bigger lattice than what we're showing you here. So this is just symbolic, just so we can show everything. Okay. How do we solve the Schrodinger equation? Time-dependent Schrodinger equation. We have a time derivative, first order, second derivative, space. We just use Taylor expansions. Expand the wave function, express the time derivative, space derivatives in terms of central differences. So it's a central difference approximation. And what we'll find is that the probability, which is the real part squared, imaginary part squared, has increased in order of accuracy compared to the wave functions. We get higher probability, higher order precision for the probability than we even get for the wave function. And we do this by using 3 different times on this grid for the probability row. We'll just use, as we see here in the algorithm diagram, we'll just use 2 times in order to solve for the wave function, but we'll use 3 times for the density. So this is extra order of complication in order to get better algorithm, in order to get better precision. And you can ask yourself, as I did, is this really legitimate? Should, don't we have to evaluate the real and imaginary parts of the wave function at the same time for it to be the same wave function? And the answer is, well, we're just doing an approximate solution. In order to be a good approximation, the approximation should get to the right answer, the exact answer, if you take the step size equal to 0. But as the step size goes to 0, the half step and the full step coalesce on top of each other. So delta t equals 0 gives us the usual expressions for probability. Okay? So it's okay. In the limit it should work. So here in equation 1 and 2, we have our algorithm. And you've seen algorithms like this before. They need to be solved simultaneously because you need, in order to determine the real part of the wave function, you need to have the imaginary part as well. And the imaginary part is determined by the real part. So they have to move ahead simultaneously. Again, we can say, okay, one of these subscripts is superscripts and subscripts. One is time and the other is position. We can see here this is taking us, it's taking us ahead 1 and all these from the present time. So this is the time variable, and all these other times, 1, 2, 3, here, it's all one time, okay? And this is space. So present position, there's the present position, 1 to the right, 1 to the left, right there. So these 3 positions, 1 time step back, lets us predict the wave function ahead. And the same thing for the real part and the imaginary part. It looks like they're at the same steps, but actually we've set it up so that the imaginary part's a half step in time different. Okay? So it's a little bit different. And if we look at the algorithm, the expression for the density, what we say is, aha, for integer time steps, integer values of t, we use one expression here for the row, r squared plus I at one time and times I at a different time. And for half integer time steps, we use another expression given below, I squared, there, real different. So what you see here is 3 different times. That's time 1, time t, second time t plus delta t, and a third time there, t minus delta t, or delta t over 2. And by having this sort of peculiar combination, and notice that both of these expressions, when delta t goes to 0, is just r squared plus I squared. But by having taken the liberty of having another degree of freedom in evaluating I and r at different times, we can get cancellations in the error. So we have, in some of our work, we've been able to get 13 to 15 decimal places of precision with this method, which is very high. It takes very small time step, but it can be as precise as you want that way without round-off error killing you. So this is the algorithm we'll use, equations 1 and 2 here. That's the hard part. From now on, things get pretty easy. Let's look at the solutions. Okay, so we're talking about the code. Okay, and I'll show you some examples now of the code and what it looks like. So here's the code. Let's tell you what it is. So the sample code we give you has the wave function real part, wave function imaginary part, 750 approximately space nodes, so not too many. You could use more, but it's good enough for to see the effect with some precision. It has a second coordinate, second indice, which indicates the time, present, future, how we move ahead. What's the initial condition? The initial condition is that at time 0, we have the real part of psi, and the imaginary part of psi, we need a time t minus 2. The initial condition was that we have that wave packet. We had a Gaussian times a plane wave. Okay, so no time dependence because t equals 0. That was the initial condition. So we put that in, as we see here, in the first slot in the real part and the first slot in the imaginary part. Well, even though the first slot in the real part indicates time 0, the first slot in the imaginary part corresponds to the staggered displaced time of delta t over 2. So that's the difference. Okay. The boundary conditions, that's on the space part of the wave function. For our sample code here is that on the boundary of the box, the wave function vanishes. You can have other ones, periodic boundary conditions, make sense just as well, makes the wave packet continuous, so it'll go around in a circle. This makes the wave packet bounce off the walls. So remember that, we'll see it bounce off the walls. And then the time increment is the time step over 2. And you need a lot of steps. You need small time step, about 5,000 steps. So here's the code. It's here someplace. Right there. So there's the code, and it's pretty much what we've told you. 300 is the maximum x values, delta x 0.04, just some numbers. K0, that's the original momentum of the particle. And then the algorithm is quite straightforward there. So there's the real part of the algorithm, and there is the psi squared, and there's psi imaginary here someplace as well. Down below, here's for the imaginary part. Okay, so the two are done, are there in the code. It's a fairly short code. And what happens? Well, here's a sample. So this is an applet written using the same code, same idea, and it's one of the classic ones. If you look at one of the quantum mechanics texts from the 1950s, Schiff, this was the example he used in the book. It took 50-odd hours at the Princeton Penn Supercomputing Center at the time to do it. We could do it in no time here at a desktop. So here we have our initial wave packet, and we can change its momentum. I'll keep it pretty high. And here's our barrier. This is a repulsive barrier. We can make it a big attractive barrier, whatever you want. We'll just start it. And you see the wave packet coming in, hitting the edge of the barrier. You see these little ripples when a reflected wave begins, and you see a tiny reflected wave coming back here, and here's the transmitted wave. Then it hits the wall, and it's going to break up into lots of little Fourier components, which bounce back and then recombine and come across again. So if we stop this, and the trick with this, if you get for the momentum, I'll lower the momentums. If you get the momentum and the wave packet depth just right, you can get like half a wave function in the well exactly. It tends to get trapped. So let's see if we can find any trapping. Let's make the well a little bigger and see if it looks different. You can see the well coming in, and actually if you use a very small time step, you get even fewer of those ripples. So some of that is just purely noise. You're getting the well here. It's not bouncing back very much from the second, hitting the second edge. You can see a little bit bouncing back there. Okay? And transmit it. Stop. If you make the well a barrier, and we'll get barrier penetration at some point, but maybe not very much, you can vary this. So this is the kind of experiments you should do on your own with your own algorithm. So here we should get some barrier penetration, maybe not much. We're getting some inside. Most is being reflected. Very little is getting through. Okay, so we could stop that. If we increase the momentum of the wave, we should get much more going through. Looks like we're getting more coming through. It is. It's weakened, and some of it gets bounced back from the second wall, but there's transmitted and reflected wave from the barrier. Okay, so we should get to work. So that's what you're supposed to do. If we look at some other examples, what else you're supposed to do? Some animations. Okay, so here we have a variety of animations you can do. One of the ones I like, and I'll show you here, is you can do a single slit. Okay? I'll leave that for you to see. A wave packet going through a single slit, you should see diffraction, interference effects. Here we have a double hump wave packets going through two slits, and you can see there's interference as they hit the wall. They then bounce it back. They now hit the outside of the box, and that causes them to really break up. So this was produced with an OpenDX. So this is wave packets, after all. Okay, so what should you do? So you saw that. In order to produce an animation, you have to have the density. So we only store in the computer 2 times, present and future. So each time you calculate the wave function in the future, you also compute rho, r squared plus I squared, but with that funny time translation, and you write it out. Except if you do that for every time step, you'll have much, much too much data, and it'll be barely see any effect, because we use a very small time step. So really, you wait every 200, 300, sometimes even 500 if you're using a lot of times, very small time steps. Wait that many times, and then output the density to a disk file someplace so you can store it. And then you can create your animation afterwards. I don't recommend trying to do the animation live at the same time if you're going to have very high precision. I think our Python code does that, but it's not the highest precision. Then either make a surface plot, and I'll show you some of those soon, density as a function of position and time, or an animation, which I've just showed you now. And what you need to do is check how good is the integral of rho of x from minus and plus infinity. How constant is that? So what you need to do is for every single time that you output, calculate this integral. It's not hard to do. You can use Simpson's rule because the time steps are uniform rather than Gaussian, quadrature. So just use Simpson rule, just add them all up, and it should be constant to some high precision. And then try to answer the question, explain, why does the wave packet tend to break up into those little pieces when it hits the wall? So let's go ahead and see. There's some other assessments you can do. Okay? You can look at a potential, like we had a Gaussian wave packet inside a harmonic oscillator. Now, since the harmonic oscillator has as its solution a Gaussian, this wave packet tends to keep together very well. So why don't you try putting a Gaussian wave packet inside of a square well potential, okay, or some other potential, and see how it distorts, how it disperses. Another generalization is to say, well, we just solved the one-dimensional Schrodinger equation. You could also solve a two-dimensional Schrodinger equation. You can have space and time. So here we have a picture of a parabolic cylinder, tube. Okay, it's parabolic in the x direction, and it's just a cylinder in the y direction. So if you send a wave packet into this mess, and here's an equation that actually describes this tube. This is a potential in two dimensions. You start with a two-dimensional wave packet, two-dimensional Gaussian. You can see it here, time 100, 300, 500. It's moving along, it's moving uphill, then it's rolling back down the hill here, and as it does so, some of it gets reflected, broken up in different ways. So this is a two-dimensional parabolic tube. Notice that it's a Gaussian wave function. It's parabolic, so it's harmonic oscillator-like in one direction. That holds it together. But in the y-coordinate, it's not harmonic oscillator-like, potential, constant, and that tends to disperse the wave packet. Very interesting. Okay, so here, what we have is another example, and I'll show you movies of this in a moment. This is another example of the Schrodinger equation, except for two particles. So take a look at this. So this is a optional, okay? This is a real extension, and if you're having trouble understanding the one-particle time-dependent Schrodinger equation, forget about this. So what this is saying is, what if I have two realistic particles, two confined quantum particles, and I smash them into each other? What happens? Well, the answer is you have two wave packets, one for each particle, or you have a wave function which should be something like two wave packets colliding with each other. Easy to say. How do you solve it? Well, you solve it with a wave function for two particles, and that's psi of x1 and x2 and t. So this is a wave function that you hardly ever see in quantum mechanics because it has the actual two variables there, and we're not separating it off into just relative and total, which we could do. In order to have the Schrodinger equation solution, we're just solving x1 and x2 coordinates, the two particle coordinates, separately, and then we have a interparticle potential, just a function of the difference. Okay, so we can again look at this solution, and if you look at the solution here, and that's what you see here on the chart, you have this problem. So here we have x1, okay, one coordinate here, so that's x1, and here we have x2 running this way, and we start off with at time 0, so this is t equals 0. We start off with a wave packet. So we have the two particles. One particle's at x2, the other one's at x1, and then they collide. Well, and here's the collision happening. Here you can see, if the wave packet's breaking up, this is the two particles moving off. But this is very hard to see because we're just not used to visualizing a wave function of two coordinates and simultaneously time. Okay? So what we've done in creating some movies for you to look at soon is to say, let's look at the density of particle 1 by itself by integrating out over all of space. This should be dx2. Okay? Integrating out the coordinate of the other particle, and that just gives us the density of 1. We'll also look at rho of x1, of x2 rather, by integrating out dx1. Okay? So we just eliminate the other particle, integrating it away, and then we should get movies. Okay. So here's a web page, an applet page. You can see it on the web. And what you're seeing here immediately, this is the classic problem from Schiff's book here, which we just saw an applet of a wave packet hitting a well, bouncing off it. Some here gets trapped inside if we get it just right. Here we have two wave packets, and they should be colliding with each other, but I think they got tired. So let's look at some of a movie here. We have many movies, and I'll just pick out one which I hope is here. Okay, so here we have each density, two particles colliding with each other, two separate particles, two wave packets interfering, and what you see is they're attractive. When they overlap, they sort of suck each other in, they do a little dance, they come down, and then you get a reflected wave from each, but the reflected wave goes off, captured by the other wave packet. So it's a quite amazing and surprising result. It's the solution of the Schrödinger equation. You can see here some interaction when they hit the wall, and of course, if they break up when they do hit the wall. And right there, you see, the full wave packets breaking up. So this is an extension. This is much harder than what you have to do, but it's a challenge. If you feel up to it, go ahead and do it. So what have we done? We've said that the time-dependent Schrödinger equation is another wave equation. We can solve it by moving ahead step by step in time, leapfrog method, just like we have other wave equations. And in this case, in order to get better precision for the probability, we make a more complicated algorithm in which the real part of the wave function and the imaginary part of the wave function are at slightly staggered times. But think of it, this is a wave. It's a complex wave with two parts, and so we use that complexity in order to maintain good precision. And we'll see shortly when we solve electromagnetic waves that we also have more complicated waves, and we'll also use different times for different components just to get better precision. So, enjoy quantum mechanics. Do not feel that you have to only solve the time-independent eigenvalue problem. Scattering is actually much more challenging, much more interesting than these bound states. Go ahead and look at some scattering. Bye-bye.